Dear children, today we are going to discuss the nucleophilic substitution reactions. Myself, Dr. Digna Varghese. Nucleophilic substitution reactions. Depending upon the kinetics, nucleophilic substitution reactions are of two types, that is, bimolecular nucleophilic substitution reaction and unimolecular nucleophilic substitution reactions. The mechanism that predominates depends upon various factors such as the structure of the alkyl halide, reactivity, and the structure of the nucleophile, and the concentration of the nucleophile. Here we are going to discuss bimolecular nucleophilic substitution reaction in detail. Bimolecular nucleophilic substitution reaction, that is SN2. Here you can see a reaction between methyl bromide and hydroxide ion to yield methanol and bromide ion. It is a typical example of SN2 reaction. Here you can see the nucleophile, that is OH-, which attacks to the substrate, that is methyl bromide. The negative charge of the nucleophile attacks to the carbon, and here the bromide ion replaces by the nucleophilic attack and forming the product methanol, and the bromide act as the leaving group here. Okay, here you can see the kinetics of the reaction. That is, it is a kinetically second order reaction. That means the law of the reaction, that is rate is equal to K into concentration of the substrate and concentration of the nucleophile. So the reaction depends upon both the concentration of the nucleophile and the substrate. So it is a second order reaction. So the SN2 means bimolecular nucleophilic substitution reaction. The SN2 means substitution nucleophilic second order reaction. Okay. So the rate is equal to K into concentration of the substrate into concentration of nucleophile. So it is a second order reaction. So the rate of this particular reaction, that is rate is equal to K into concentration of methyl bromide, that is substrate here, and the concentration of OH-, that is nucleophile in this reaction. The SN2 reaction, the mechanism proposed by Hughes and Ingold. SN2 stands for S stands for substitution, N stands for nucleophilic, and 2 stands for it's a second order reaction by kinetics. Here you can see the nucleophile attacks to the methyl bromide and forming the product methanol and the leaving group bromide ion. The OH- attacks to the rear side of the substrate molecule, that is the nucleophile attacks the carbon from the sterically favorable rear side or the backside attack, which displaces the leaving group. Here you can see the three types of attack when a nucleophile attacks to the substrate. In this way, this is a backside attack of the molecule, and this is the side attack to the molecule, and this is the front side attack. Here in this SN2 reaction, the nucleophile attacks to the backside attack, which prefers the backside attack. That means it is a sterically favorable side attack. So it displaces the leaving group, that is bromide, and forms the product here, that is methanol. It is a concerted mechanism, That means it follows a single step reaction. In this reaction, there is no intermediate formed. It is a direct displacement mechanism. Here, OH- attacks to the substrate molecule. The leaving group displaces from the molecule and forming the product. It is a single step reaction. It follows the concerted mechanism. It is a direct displacement reaction, and it is also there is no intermediate formed. Now we are going to discuss the Hughes and Ingold mechanism of SN2 reaction in detail. The reaction between methyl bromide and OH- ion. Here you can see this is a slow reaction and forming. The OH- attacks the carbon from the backside and displaces the leaving group through a transition state. The transition state in the formation of which both the substrate and the nucleophile participate. The transition state you can see here in which the carbon is partially bonded to both the incoming nucleophile and the leaving group bromide ion here. So we know the SN2 reaction or SN2 mechanism is also known as the direct displacement mechanism because the bond forming and bond breaking occurs in the same step through a transition state. So, it is a state in which COH bond is not completely formed and CBr bond is not completely broken. So, this is the transition state in which all the bond angles being 120 degree. Here the three hydrogen atoms, the bond angle is in 120 degree. While the OH and Br bromide ion lie as far apart as possible on either side of this 120-degree plane. Okay, so the bond breaks to form the product and the leaving group. Here you can see the nucleophile is OH- and the substrate is methyl bromide, and here the reaction proceeds through a transition state and the product is the methanol and the leaving group is bromide ion. In Hughes-Ingold mechanism of SN2 reaction, the backside attack by the nucleophile will be reflected as an inversion of configuration. That is known as Walden inversion. So, the reaction, the substrate configuration is inverted here after forming the product. That inversion is known as Walden inversion. Stereochemistry of SN2 reaction. We know it is a undergo Walden inversion. This type of inversion is first seen by Paul Walden in 1896. That means the nucleophile attacks the substrate carbon from the backside. Okay, here you can see the nucleophile attacks the carbon through backside. One lobe of the sp3 orbital of carbon, that is you can see here the lobe of carbon that is attached to the or overlap with the lobe of orbital of leaving group, that is you can see here as green, and carbon lobe is you can see here as yellow in color. So one lobe of the carbon that is attached to the or overlap with the leaving group and other lobe is free. That lobe is overlapped with the nucleophiles orbital. That overlap with the nucleophiles orbital. So it is the attacks from the backside. So inversion of configuration occurs. Such inversion is known as Walden inversion. That means the configuration opposite to that of the reactant. If the configuration of the molecule is R, after nucleophilic addition takes or substitution takes place, the configuration changes to S. Okay. So it is S means that a stereochemical inversion takes place. Here you can see the hydrolysis of 2-bromo-octane and forming the 2-bromo-octanol. Okay, here the minus 2-bromo-octane which is attacks the backside to the substrate molecule. That's a slow reaction. It undergoes a transition state. Here you can see bond forming and not takes place completely here, and bond breaking not takes place here completely. So the reaction between the bromo-octane and the hydroxyl ion through a transition state and forming the octanol and the leaving group. Okay, so the hydrolysis of 2-bromo-octane forms octanol, but the configuration here is minus, here it is plus. So inversion of configuration occurs. The state of hybridization. The state of hybridization of carbon goes from sp3 to sp2. Nucleophile comes on one side of the substrate and bonds to the carbon, and the halide ion departs from the other side. Okay, so the configuration undergo an inversion, that is stereochemical inversion. An open umbrella turns inside out in a sudden wind. So like this, the molecule is inverted here. That is known as Walden inversion. Factors affecting reactivity in the SN2 reaction. The first one is the nature of the substrate or alkyl group, that is by the steric effects. Here you can see the order of the reactivity of the substrate molecule. Methyl halide greater than primary alkyl halide greater than secondary alkyl halide greater than tertiary alkyl halide. Methyl halide, the molecular formula is CH3X. Primary alkyl halide is CH3CH2X. Secondary alkyl halide is CH3 twice CHX. Tertiary alkyl halide is CH3 thrice CX. Here you can see in this molecule the carbon atom attached to the 3 hydrogen atoms. Here you can see the carbon atom attached to 2 hydrogen atom and 1 methyl group. Here you can see in the case of secondary alkyl halide, carbon atom attached to 2 methyl group and 1 hydrogen atom. Here in the case of tertiary alkyl halide, the carbon atom or the halide atom attached to the carbon which attached to the 3-methyl group. So it is steric effect is more in the case of tertiary alkyl halide. Steric effect is somewhat lesser than that of the tertiary alkyl halide in the case of secondary alkyl halide. So least steric effect in the case of methyl halide. So the steric effect is less. The reactivity of SN2 reactions is higher for methyl halides than for primary alkyl halide and the least for tertiary alkyl halide. Here you can see the nucleophile attached to the backside of the substrate molecule. Here the R dash, R2, R. In the case of methyl halide, these are hydrogen. In the case of secondary primary alkyl halide, R is R dash and R is hydrogen, R2 dash is methyl group. Okay. In the case of secondary alkyl halide, R is hydrogen, R dash and R2 dash are methyl group. If it is a tertiary alkyl halide, R is R dash and R double dash is methyl group. So it is more sterically hindered one if it is a tertiary alkyl halide. There is no SN2 reaction takes place. If it is a primary alkyl halide, it is the R double dash is hydrogen, R is hydrogen or R dash is methyl and so on. Okay. And the reactivity is somewhat higher when compared to tertiary alkyl halide. So the reactivity for SN2 reaction is higher for methyl halide than primary alkyl halide, then secondary alkyl halide, and there is for the tertiary alkyl halide, it is unable to undergo SN2 reactions due to steric effect. Nature of the leaving group. Weaker the basicity of the leaving group, the better is its leaving group ability. Here the basicity order of the halide ion is that I minus less than Br minus less than Cl minus less than F minus. We know the weaker the base, the weaker is its bond with the stereochemical carbon and the easier it is to break it. So the leaving group order is I minus greater than Br minus greater than Cl minus greater than F minus. Therefore, the alkyl halide which undergo SN2 reaction more fastly with Ri greater than Rbr greater than Rcl greater than Rf because if it is a weak base, it will bond weaker with the carbon center so that if a nucleophile attacks to this particular substrate, the leaving group can easily displaced from the substrate molecule after nucleophilic substitution takes place. Another one is the nature of the nucleophile. Nucleophiles are Lewis bases. That means it has a negative charge. So stronger the bases are better nucleophiles. So here you can see methyl CH3 minus greater than NH2 minus OH minus greater than F minus. So it is the order of relative nucleophilicity. Greater the nucleophilicity, greater is its SN2 reactivity. The reactivities of the nucleophiles increases in the order of increasing nucleophilicities. Nucleophilicity means it is a measure of the how well a nucleophile share its electrons to the non-bonding electrons with an electron deficient center other than a proton. So, nucleophiles are Lewis bases. It is a stronger bases are better nucleophiles. So, it can donate electrons to the electron deficient carbon atom. So greater the nucleophilicity, greater is its SN2 reactivity. Thank you for your attention.